Welcome everyone. And again, if you have any questions, you can either save them to the end, or I'm fine with just stopping and answering questions as we go. But I've got about 46 slides, so I'm going to buzz through them pretty quickly. Again, if there's any questions, please feel free to just pop in there and let me know. Okay, so again, I'm going to be talking about activated sludge. This is stuff I've kind of geared this presentation more for the grades 4 and 5, the more advanced ones. I didn't get heavy in the math. I figured you guys have already been through the grade 3, so you know pretty much the math, but some of the formulas I'll talk about, but you know, big long math examples, I kind of skirted around those because I wanted to get more of the information that's just more current, especially in nitrification and the activated sludge process. So again, the slides I believe are available in PDF, and you'll be able to download these, and hopefully they'll help you study for your exam. This is me, I'm Chief Operating Officer at Silicon Valley Clean Water. I've been here for 10 years this year. I've got over 35 years in wastewater treatment plant or treatment, and also in potable water treatment. I've worked in the industry for a long time, all here in Northern California, and I worked for Veolia Water for over 22 years. So I have a lot of experience nationwide too, different treatment plants and things. So again, use me as a resource, put me as part of your network. I'm happy to answer questions. I also teach classes at Gavilan College in their water management program. So may see you guys there. So activated sludge, what is it? Well, activated sludge, the reason they talk about it being activated is it refers to, it's a living organism. It's got bacteria, fungi, protozoa, and that's what makes it active. That's that word, activated. And then the activated sludge process is a biological process that uses microorganisms to speed up the decomposition of waste. And mainly the waste that they're looking at are the biochemical oxygen demands, and the COD is the chemical oxygen demands. Those things that are colloidal. Most of the solids have already been removed in your primary process prior to going into your activated sludge process. So it's just looking at those sugars and starches that are very, very difficult to remove from the wastewater. And that's why you need this biological process to do that. So this is a pretty handy chart, and most of you have probably seen this. It's been around for a long time. I just added a few pictures to it, but I refer to this often. And at the bottom, if you look, there's certain things you'll see like SVI, your sludge volume index. If you have a high SVI, then you're probably in a microscope slide of your activated sludge, you're going to see more free swimming ciliates, flagellates, maybe some amoebas. And you're going to basically be on the younger side of your solids, of your activated sludge. As you start getting older and you start seeing nematodes and more rotifers and more complex organisms, your SVI is going to be on the low side. Same with your food to microorganism ratio, your FDM goes the same way. Your MCRT and your SRTs, your mean cell residence time and your sludge retention times will go the opposite direction. The younger organisms that you'll see, you have a low MCRT or sludge retention age. And then the older rotifers, nematodes, those kind of things that start popping up in your microscope slide, you'll start seeing your sludge aging, also your MCRT increasing, but what you're also going to see is you're going to see settling issues. Good settling is right in the middle. That's where you want to be. That's where you want to maintain. And generally the organism I'm looking for in activated sludge are stock ciliates. When I see a good colonies of stock ciliates, I know I'm in that sweet spot for good settling. If you get on the younger side, you'll get straggler flock. If you get on the older side, you'll get pin flock. So again, just it's a quick reference chart. I actually have it printed it's in our lab and it's in our operations room, and guys refer to it when they start seeing things in their secondary clarifiers. And, you know, we all know what the good bugs are. If you've been in the industry for a while, especially those of you taking 4s and 5s, you're going to want to see good stock ciliates, and you're going to want to see rotifers. That tells you you're in that good age of your solids, of your activated sludge, that you should get good settling and get good treatment. These guys here, they're prolific. They're looking for that BOD. And if you have a good, healthy environment, these guys will proliferate and they'll do a good job for you. When you start getting a little older, you'll see other higher formed microorganisms coming in, and then you'll start to see difference in settling. And then those of you that have had the unpleasant experience of the bad microorganisms that you don't want to see, and that's a filamentous bacteria. And generally these are low DO situations, usually low FTMs. So when you get in those situations and you start to see these guys show up on your microscope slides, your environment isn't right. You're out of balance, and you need to take some kind of action, whether it's to reduce your MCRT, increase your oxygen levels. Sometimes that'll work. Some places elect to chlorinate the RAS, and the RAS doesn't actually kill the microorganisms. What the RAS does is it actually breaks the chains of the filaments so they can't stick together. But you have to be very, very careful when you chlorinate RAS. You know, you can over-chlorinate and kill the good bugs that you want, and you can under-chlorinate and it's absolutely ineffective. And then if you continually chlorinate, these guys can actually develop a resistance to it. So it's better to really work on your process control, set your targets, stay within that range that you want to, and have your DOs proper, have your MCRTs or your SRTs, whatever you use for your process control, right in your target ranges. And these guys should not appear.
Robert, a quick question for you.
Yes.
You had mentioned chlorination there. Mm-hmm. Is there like some, if we did have to chlorinate to get rid of some unwanted microorganisms, is there like some level, like 1 part per million, 2 parts per million, 3 that's good or bad? Some range?
You know, it's a good question, and it's a question that's kind of difficult to answer because it all depends on where you're at in your activated sludge process. If you're having like low inventories, let's say your mixed liquor suspended solids is around 1,000, you don't have a lot of inventory and it's kind of on the thin side and you're young already, if you hit it with a heavy dose of chlorine, you're going to do some damage. But if you're in the longer end and you're in the higher MCRTs and SRTs, you're going to have more, you know, microorganisms there, and you can increase that RAS a little more. Most likely you're going to be in that longer, older sludge when the filaments start showing up. So, I mean, there's different trains of thought here. Some people say, hey, I want to ease into it. I want to hit it with chlorine, do my microscope slides, see what shape the activated sludge is in. And then if I can, I'll increase it and I'll just kind of step it up. That takes a while to do. Sometimes it's not as effective, but if you're on the thinner side, that's the proper approach. If you're longer in your MCRT and you see these guys show up and you have some serious problems, you know, some of the guys have been in the industry a long time, they refer to it as roast them and toss them. You hit it hard. I mean, you're looking at 50, 100 ppm.
Wow. Okay.
Very short period of time. Mm-hmm. And then you're wasting like crazy to get it out of your system and then watching things closely. But you hit it really hard, short period of time, get rid of it, and then slowly bring your activated sludge back up. So again, it all depends on where you're at on that spectrum.
Okay. All right. That's helpful. Thank you.
Mm-hmm. So the basic needs of a healthy activated sludge are pretty simple. You need food. You got to feed them. And the food is in the form of BOD. You need an ample supply of oxygen, and you have to be able to control that oxygen that you can put into your activated sludge. And also you need good mixing. You want to create that good homogeneous solution for the food and the air and the microorganisms all to be coming in contact continuously. And also you have to have the ability to maintain the desired activated sludge inventory. And what I mean by that is you need to control the pounds of activated sludge that you have in your system. And that's where your MCRT or your SRT control comes in, because that's the formulas that you use. What's my inventory? How much activated sludge do I have? What's my MLSS or MLVSS, however you do it? And that's what you're controlling. And you're trying to maintain a certain inventory. How many pounds of bugs do I have in my system? That's all controlled through your wasting rates. So again, you have to have the ability to change those wasting rates. You need food, you need oxygen, and you need good mixing. And this is just a picture of a typical conventional activated sludge process where you have your primary effluent coming in. It goes into your activated sludge tank, or your mixed liquor tank, as some people call it. You're adding air. Primary effluent has the food. You're mixing in that mixed liquor basin or your activated sludge basin. Then it goes into your secondary clarifier. All your microorganisms should settle to the bottom. You're collecting those on the bottom, and you're returning those in your RAS and your return activated sludge back into your activated sludge system. But off of that is where you pull your wasting. And the reason you want to do that is your RAS generally is 2 times the concentration of your activated sludge. If your activated sludge MLSS is 2,000, your RAS should be close to 4,000. And by being able to waste the higher concentrated activated sludge, you'll be able to pull more out of the system with less flow. So it's the better way to do it rather than trying to waste out of the activated sludge basin itself. But this is just a typical conventional activated sludge system. And this is just, I like to just review a little bit where your MLSS is a concentration of suspended solids in the mixed liquor of an aeration tank. And that includes everything. That's your organic or your microorganisms. It's also your inorganic. If you got any grit in there, if you got any small sand particles, any of those kind of things, that will show up in your MLSS. Your MLVSS, or your mixed liquor volatile suspended solids, that is where you take your, if you're in the lab, you take your MLSS sample, you dry it, you weigh it, then you put it into a muffle furnace at 550 degrees C, and everything that's organic in there will burn off, leaving only the inorganic portion on the weighing paper. You weigh that and you subtract it from your mixed liquor, and that will give you just pretty much how much microorganisms you had in your activated sludge system. And that's important because when you do your food to microorganism ratio as one of your process control parameters, you want to make sure you use the MLVSS, because that's the actual that's closer to the amount of actual activated sludge microorganisms that you have. And you can do your BOD, and that's a food coming into those microorganisms. If you use your MLSS, you can have all that inert stuff that's really not doing anything with the BOD, and it will throw that ratio off depending on your collection system and how much, I&I you're getting, how much settling, how much sand and grit and those kind of things are coming into your system. So again, use the MLVSS when you're working with your F-to-M ratios. Sludge age, some folks prefer to use it as their process control parameter for their activated sludge. And sludge age is an indicator of the length of time a pound of solids is kept under aeration. And there's the formula for sludge age in days. So it's your suspended solids under aeration and your suspended solids that are added per day, which is your TSS and your primary effluent So that's how you can figure out your sludge age. Remember, that's a length of time 1 pound of solids is kept under aeration. And these are just some of the parameters. A high rate activated sludge system, the sludge age is 1/2 to 2 days. You can operate at the highest loading for highest F to M at a high rate. A conventional rate, most common operation, you're going to run the F to M about 50% of the high rate. So anyway, the important thing is it's about 3.5 to 7 days. And then if you get into extended aeration, you're looking at greater than 10 days of a sludge age. Now, the mean cell residence time, or the MCRT, is average time in days that a microorganism, a single microorganism, will spend in the activated sludge process. Not a pound, a single organism. And for here at Silicon Valley Clean Water, we use MCRT as our process control parameter, just because I like it, because it has more, I say more meaning, but it also takes into account your wasting rates. It also takes into account the solids that are lost in your effluent and your secondary suspended solids that are actually being discharged, and also your inventory, what you have in your secondary clarifiers and your activated sludge, your aeration basins. So again, to me, it's more of a representative parameter, and also it changes a little faster than your SRT will. And then some people factor into that your solids retention time. And that's the expression of the average time in days that the solids, and they're talking about solids as a whole, will spend in the activated sludge process. So you'll see SRT, the solids retention time. The other one I didn't put on here, I kind of missed it because we were just talking about it this morning. You'll see HRT, which is a hydraulic retention time. The SRT is just dealing with your solids. The HRT is the hydraulics. It's how much flow are you coming in. And generally, when you're talking HRT or hydraulic retention time, you're talking about your secondary clarifiers. Am I hydraulically overloading them? We just had that issue here at our plant where we started seeing the secondary effluent turbidity started to increase. Effluent suspended solids started to increase. What's going on? We ran some calculations. We do have a process control program, and it said, hey, your SRT is your HRT, your hydraulic retention time, and our SRT, our solid retention time, was long. It was beyond our control point or our targets. And that was because we had 4 secondary clarifiers in service. Our flows had started to drop off because of what weather season's coming to an end. And then what we see is the solids are sitting in the clarifiers too long. So when that happens, you start to denitrify, you start to do a lot of other things, and that added to that increase in turbidity. What we did, we took 2 clarifiers out of service, and that's our summer operation. So that will balance, get our hydraulic retention time back up where it needs to be within our target, and also our solid retention time. But we have to readjust the RAS when we do that. So it's very important to look at these parameters and have these parameters in your process control programs. And this is something that every operator does at some point in their career. They do a 30-minute settleometer, and my operators are going, I do this test and I have no idea what it means. And it's like, okay, so I'll sit with them and say, okay, let's talk about this. You put your activated sludge sample in there, you stir it up, you start the timer, and you let it sit for 30 minutes. What you're doing is you're simulating what's happening in a secondary clarifier. So is the solids all going to settle nicely and uniformly and slowly, and then have a nice level surface to it? That's exactly what you want. You want a nice dense sludge blanket, because that's what's getting picked up as your RAS, and that's getting returned to your activated sludge system. Also, the water on top that actually is what's being displaced and going over your secondary weirs is going to be nice and clean. Or Do you have pin flock, like the second picture in the middle? Well, that's telling me it's not settling all that great, and I've got some issues going on in my activated sludge system. Or after 30 minutes, the stuff split. And what happens there is you'll see denitrification happening right before your eyes. And that's what we saw. When we did our settleometer, we saw it split, and it wasn't at 30 minutes, it split at 32 minutes. And if the guys were a little too quick and poured it out, they missed that. So I go, let's let it go 35 minutes. Let's see what it does. And at 32 minutes, it split. So we started to denitrify. And when you see that, you go, my HRT, or my hydraulic retention time, and my sludge retention time is too long in my secondaries. So this is a very important test. And if you train your operators what to look for and go over with them what it means, then they're going to start seeing this stuff, and they're going to start paying more attention to this, rather than, this is a task I was assigned, I did it, I wrote down the results, and I checked the box, I'm on to the next task. I see some guys laughing, and they know exactly what I'm talking about. So I've done it myself. But once I learned what it does and the importance of it, I started paying a little more attention. And there's another factor that we look at, and engineers really focus on this when they're designing treatment plants, and that's your sludge volume index. And it's an indicator of the settability characteristics of the MLSS. How is it going to settle? Is my tank big enough? Am I going to provide enough hydraulic retention time with the tank that I'm going to design? So you always want to make sure you take a look at this. Also, it's an indicator of what's happening in that, should be happening in that settleometer test. So we also have this as one of our process control parameters, and we watch our SVI very closely, and our target is to keep it below 150. Other treatment plants I've seen, they want to keep it under 100, 120. And there's some that have absolutely beautiful water, and their SVI is over 200. So every treatment plant's a little bit different. You just need to pay attention. You need to push your plant and see where the sweet spot is. So there's really no good rule of thumb in your O&M manual. The engineers that design it will design it to a certain SVI. That's kind of your target, but you'll find that it'll be a little less than that or a little more than that. It won't be right on. And the true indicator is your secondary effluent. How clean is it? And how well is my sludge settling? That's when you know you're in that your sweet spot for your SVI. And then these are just some terms that you guys are, I'm sure, already familiar with at this rate. And your RAS is your return activated sludge, what you're returning from your secondary clarifiers back into your aeration basins. And then the WAS is your waste activated sludge that you're basically pulling out of the system to manage your inventory of activated sludge. And one of the things, depending on this is another reason I really like to use the MCRT, is you can manipulate the MCRT calculation or the formula to basically get your formula for your wasting. You can say, hey, my target is an MCRT of 2 days, 3 days. You can plug that in. This is what my actual mixed liquor volatile solids is today. And this is what my effluent TSS was yesterday. And it'll actually tell you how much waste activated sludge you need to pull out of the system to maintain your target 2 or 3 day MCRT. So again, this is just an example of the different process control parameters and what you can do with them and make it meaningful. But you have to be consistent. You can't use SRT, your sludge age one day and use MCRT the next day. It has to be consistent. You have to use one or the other. And this is something too, I have a degree background in biology, and one of the important things I've gathered studying activated sludge is there's 2 properties that they use to assimilate their food. How does a bacteria assimilate BOD? How does it get rid of it? Well, there's 2 different ways. One, there's adsorption with a D, And that is where it's actually going to stick to the surface on the outside of the bacteria or the microorganism, and it can assimilate it through its cell walls. The other is absorption. And that's taking it in. You're actually absorbing it in through the cell wall into the bacteria itself. So absorption, sticking to the outside, and it's able to assimilate it through. And then the other is absorption, where you're actually taking it right through the cell wall, right in, and then the bacteria or the microorganisms dealing with it that way. So that's two properties, physical properties that bacteria use to get their food into their body to where they can assimilate it. And then there's another term that you'll hear a lot, and it's oxidation. In oxidation, if you open up a chemistry book and you look up oxidation, you're just going to just have that blank stare, like a deer in the headlights. It's very complex. There's oxidation and there's reduction when you're dealing with oxygen in a liquid form, and you're talking about biochemistry with bacteria or living organisms. I like to kind of get it down into simple form to where operators will kind of understand it. And basically the terms of oxidation is when you're gaining oxygen. When you're oxidizing, you're going to gain an oxygen molecule. You're going to add one to whatever molecule that is, or you're adding it to your bacteria. Reduction is the loss of oxygen. So if you have a chemical and it's NO3, nitrate, and nitrate's being reduced to nitrite and then to nitrogen gas, you're losing the oxygens. You're reducing nitrate to N2. So, and the opposite's happening where you're taking ammonia when you're nitrifying and you're adding oxygen to it. You're oxidizing the ammonia to make nitrate. So when you're going through your certification exams, just kind of keep these in mind. Oxidation, I'm gaining oxygen. Reduction, I'm going to lose it. So it just will help you, especially if there's an essay question or something on activated sludge. It's helped me in the past just to remember those two simple properties. But again, if you open up a chemistry book and really study oxidation and reduction, it's a whole entire book. There's a lot more to it. But for our purposes, this will get you through certification exam. And there's a test that we run. Some treatment plants don't. We do like to, because it's an indicator, and it's doing an oxygen uptake rate. And the operators actually do this once a week. And it's the rate at which a microorganism uses oxygen while consuming BOD from the wastewater. So basically, you're taking a sample of your activated sludge right in the beginning of your aeration basin. So you should have food in there. You'll have your fresh activated sludge after your RAS is reintroduced into the head of that basin. And you're going to have oxygen in there because you're adding air, you're mixing. It should have air, food, and activated sludge in that bottle, that BOD bottle. And you're going to do this over a period of time. And generally it's about 15 minutes. And you're going to read the oxygen levels. That oxygen probe is going to measure the oxygen levels over that 15 minutes. And what happens is you'll see it decline, which means you have a good, healthy activated sludge. There's nothing interfering. It's good, it's healthy, it's looking for food. And as it utilizes the food, it's going to utilize oxygen too, because these are aerobic bacteria and microorganisms. They need air and oxygen to live. So as they're eating the food, they're using up oxygen. You can measure this and you can see a really quick snapshot of the health of your activated sludge. If something's toxic in there and it's affecting your bacteria, maybe it's not feeling too well and it's not assimilating stuff as it should, it won't use much oxygen. And you'll actually see that in this quick 15-minute test. Also, if you have more food coming in than the bacteria, then also your FDM's off, you'll also see that in this test. So it's just a really good indicator. Yeah, some people look at it and they go, oh, well, that's just kind of waste of time. But in our agency, we actually look at this. We look at it every week. It's in our process control meetings, and we do discuss our OUR, our oxygen uptake rates. One of the things too is activated sludge operation. Getting into that now, operating the actual activated sludge system. And when the F to M is low, you have more food than you have microorganisms. What happens is you can end up forcing the microorganisms because they're going to run out of food before the end of your aeration basin, especially if it's plug flow. You have all the flow and food coming in from one end, and it just has one outlet. It's not step fed into the system at different points. By the time you get to the end of that aeration basin, these guys have no more food. They kind of ran out. Now you're going to dump them in the secondary clarifier for an hour where they got to sit there with no food, and they're not going to be too happy. They'll actually start to utilize some of their own cellular mass. It's kind of like us, when we go on kind of a starvation diet, what's our body do? It starts utilizing fat cells. Sure, we all store up fat cells. I'm actually very good at that. A lot better storing them than I am getting rid of them. But the bacteria in your microorganisms will do the same thing. So when you hit into endogenous respiration, then that's going to be a problem, and you're going to see settling issues. You're going to see your inventory start going down and not knowing why, and that's because your FDM is off. You got way too much microorganisms for the amount of food you have coming in, and that's a good indicator that you need to reduce your activated sludge inventory to match that food that you have coming in. So endogenous respiration, I have seen on certification exams, so don't be surprised if that's not a multiple choice or true false question. And then, we talked about food coming in, and now we got to supply oxygen. And how do you do that in an activated sludge system? Well, there's different methods of doing that. There's the mechanical way. And a lot of the older treatment plants have this, where they just have big mixers. Or if you have a pond system, you'll have floating aerators that are big mixers, and they mix it. And what they do is they cast the liquid out in, they splash it. And when it splashes, it'll actually grab oxygen, grab air, bring it back down into your activated sludge system. So you have mechanical aeration or mechanical ways of getting that oxygen into the water. Then you have diffused air, and you have a big compressor that's forcing air up through these diffusers, and it breaks it into smaller bubbles. And the smaller the bubbles or the finer the bubbles, the more surface area you have. And then as you're mixing this and your bacteria is in there with its food, it's much easier for the bacteria to come in contact with this oxygen source. So that's why they use diffusers. There's fine bubble diffusers, there's medium bubble diffusers, there's coarse. It all depends on how your system's designed. But these ceramic head diffusers, and then there's a membrane sock diffusers that are pretty popular. And now there's even flat panel diffusers that I've seen, some of the newer technologies. So again, this is diffused air aeration. And then there's another type, which is hybrid. It's mechanical and diffused air. And actually, this is what we have here at Silicon Valley Clean Water. And we actually have these invent parabolic mixers where the air is introduced underneath this parabolic mixer. And this mixer, you can see these little fins on the bottom of it. And this thing spins. So the air bubbles are coming up, hits these fins. The fins will actually break up the air bubbles and cast them out to the side like a centrifugal pump. When it does that, it makes a finer bubble. And then that will come up and air, the gases want to rise. So you also get a little bit of lifting action. So here you can actually mix with the mechanical, and also you're adding air into the system in a diffused way. So they're starting to see a lot of places still are in the diffused air business, and these are pretty energy efficient when you can do the hybrid, because you do get really good mixing action with these parabolic mixers also. Saved us a ton of money. We saved almost $250,000 a year in electric costs when we went from just plain mechanical mixers to this hybrid mixer. And this is just some examples of the different type of blowers, in a diffused air system or the hybrid. You need compressors, and there's different types of compressors. There's a positive displacement blowers, which are rotary lobe, which will actually trap the air in different spaces. That'll create that pressure to be able to force it out through those diffusers, because you need a fair amount of pressure to be able to push that air out through there. And these can create very high volumes of air too. You're looking for volume and you're looking for pressure. And then there's the centrifugal blowers, which are very popular. We just replaced our centrifugal blowers with the next blower I'll show on the screen. But a lot of treatment plants will have these centrifugal blowers. These were, state of the art 30 years ago. They're not as efficient is the problem. They can push a lot of air, but it takes a lot of power. And a lot of these are fixed speed. They're not variable frequency drives. They're just direct drives. So that motor, if it's 100 horsepower, you're putting, 95% of that all the time, line speed. Where if you then, like we have, go to these microturbines, and these turbine blowers are much more efficient. There's a lot less friction loss. There's a lot less drag. You can put them on variable frequency, changing the speed of the blowers themselves to match whatever your need is at that time of the activated sludge, because you need, depending on the time of day, your flows come up and down. Your air requirement's going to also kind of go with that flow. So we're able to control things better. Efficiency wise, it saved us a bunch of money also. And they're much quieter. Wow, those old centrifugal blowers, these guys, yeah, you have to have ear protection when you walk in that room. These guys, you can go down there and put your chair and eat lunch right next to it. Barely know it's on. Much, much better, much safer, and much more efficient.
From Monte,
Yeah.
is there like some typical level of efficiency differences, like the turbo blowers, like 50% more efficient, or 75%, or 10%?
Ours, I'm trying to remember. Yeah. We did a bunch of calculations, our engineering group did, because we applied for PG&E rebates on these for energy efficiency. And I believe these were 37% more efficient than the centrifugal blowers. So it all depends on your centrifugal blower and the age of them. If they're newer, they may be much more energy efficient. Ours were the original 1981 centrifugal blowers. And, we've rebuilt them as many times as we think we could. I don't think we could have gotten many more rebuilds out of them because they were just worn out. But when we did it, the calculations in the models that the engineers used for energy efficiency was around 37%. And we're actually realizing we're getting about 42% more efficient than we were, just based on energy savings, how much kilowatts we're actually using for this process. Okay. So it was significant. It was definitely has a pretty good return on your investment, which is what your commissioner board is interested in, and your plant manager, and especially your finance guy. So, as operators, there's three main things we're looking at as operators when we have an activated sludge system. What's our concern? We want to know what's coming in the plant. We want to make sure that, we don't have any toxic things coming in. We don't want a big slug of BOD coming in. We're pretty dependent on our industrial pretreatment program to make sure that those kind of things are either managed or they're not coming into the treatment plant. That can definitely upset your activated sludge system. Also, our concern and what we do for a living as operators is we are maintaining that environment to basically grow our activated sludge and maintain it. My wife refers to me as a farmer. You know, this is our livestock. It's our job to make sure that we maintain it and we take care of it. You know, that dairy cow, it needs food, it needs maintenance, you know, it needs a good, safe environment, and it'll produce for you. It's the same thing with activated sludge. And also, we're very concerned with what leaves a plant, because that's going to be regulated through our NPDES permits on what we can discharge in TSS or in BOD. So again, what comes in the plant, how we maintain our process, and then what's leaving, because that what's leaving is going to be an indicator on how well our process is working. So, and I just threw this up just for kind of your reference. I believe this is in one of the SAC state manuals for wastewater operations. I think it's in volume 1. And this is just typical parameters you see in an activated sludge system. You know, what's coming in your influent and your COD and BOD, what kind of ranges you can expect, what your primary effluent BOD and should be going into your activated sludge system, and what your final effluent BOD. And most of us are, you know, it says 10 to 20. This book was written a long time ago. This is the old volume, or I think 7th edition. Now the 8th edition, I believe that number's changed, because most of us are down below 10. And again, it's just a good reference, and it's kind of an indicator on what your activated sludge ranges that it should be operating in, and also what should be coming into your treatment plant. But the best indicator is what's in your O&M manual. Generally, right in the beginning, there's a page that shows what the engineers used to guess at what was going to be coming in, and what the how the process was going to operate, and the results. And this is, we use a process control management plan, which I encourage everyone to have. There's different ones out there. We tend to use one called HawkWIMS. It's provided by Hawk. And our laboratory has a laboratory, it's called LIMS, Laboratory Information Management System. And the lab techs will put all the results in of your MLSS, your VLS, your VSS, your BOD, all of the parameters that they're going to analyze on a daily basis. All that information goes into LIMS, and it automatically transfers into HawkWIMS. And HawkWIMS is just a database. It gets the data, it manages the data, and then you can create these unit process reports, and it'll dump the data in there. It will manage the data, and then it will give you, and we use these in our weekly process control meetings, where we're looking at our aeration basin average MLVSS. And it's like, okay, we have an upper control limit that we're creeping up on, and that is 1,050. So we set these limits and these targets, and basically it looks at this average and it says, hey, that average, you actually just passed your upper warning limit. And now, whoa, you actually passed your upper control limit. So something's wrong. You guys need to make a change. You need to increase your wasting. Those are all indicators. And you can see this is upper warning limit. We got above that for our aeration basin OUR. In our SSB 30, we have an upper warning limit where our settling was at 200 and our target's at 150 after 30 minutes. So it's a really good indicator, and it gives you a really good snapshot, and the operators can bring this up anytime. It's live, it's dumping data in there every day, and they can kind of get a good idea of what's happening in your activated sludge system. So I highly encourage people to get a process control management plan. And just talk a little bit about abnormal operations, what we might see. Rising bulking sludge. I think we've all seen this in our secondary clarifiers. What's causing that? Well, we saw in the settleometer where it split, we were denitrifying because we had too long of a hydraulic retention time and a sludge retention time. Also, if it sits in there way too long, the sludge on the bottom, your RAS, can go septic. And when that happens, you need to increase your RAS rate. You need to get it out of there faster. So those are indicators. This is an indicator. What you're seeing here, your visual, where you're seeing bulking sludge, you're seeing pin flock and crappy settling, and you'll see this in your SSB 30 if you do it every day. You'll kind of see this coming, and you can make those adjustments. Also, you can get hit with a toxic load, and we got hit with motor oil one time, and it totally covered the activated sludge basins, and it totally covered the secondary clarifiers. And we saw some significant issues with our settling during that time period until we could work that stuff out of the system. So again, this is where we can count on our pre-treatment people out there that are inspecting businesses and watching what comes into the treatment plant. So again, toxic loads can also result in those things. And we talked about Nocardia as being a bad bug. I personally haven't seen this, but I got these pictures off the internet, and I talked to a few friends of mine, and they have seen this. This is actually Nocardia out of control, where they didn't do, chlorinate their RAS, or they didn't get their oxygen rates set right back, or their MCRTs. Also, there's other things. There can be, maybe they got hit with a big slug of BOD, new business moved into town. There's other factors that can cause this Nocardia to really take off. So hopefully none of you experienced this. But again, the other part too, and I have seen this, where someone dumped a bunch of laundry detergent. It was a business, it was going out of business, and they had a bunch of stuff left over. And what's easy, no one's seeing it, it's in a warehouse, dump it down the drain. Well, they dumped a bunch of laundry detergent. And I believe that was this particular situation. This brownish color, this one over here, that's Nocardia. This one over here, I think, was a soap dump. And then you hit that with your air and your diffused air, and you put soap in your activated sludge and then hit it with air, and it makes the most beautiful bubble bath you've probably ever seen. It's huge. So this is where operators just grab every hose they can find and just start hosing and trying to knock it down. And again, this is just a quick math problem I threw in here as the F to M. I'm not going to spend much time on it because I really want to get to the next section. But if you download this, you'll be able to see this is what's known, your flow, your BOD. It gives you your aeration basin volume, your MLVSS, and the pounds formula, which is what it's all about with the F to M. And then you plug all those numbers into the calculation or into the formula, and you'll come out with 0.8 days in this particular calculation. So again, it's just kind of as an example of a math problem that you guys may be faced with on your certification exams. I want to talk a little bit more because I'm getting a little long here. I got a few more slides, about 10 more, and it's talking about nitrification and why do you need to nitrify? And it's becoming a big deal here if you're especially in the Bay Area. They're focusing on San Francisco Bay as possibly being impacted by the amount of nitrogen that's being discharged by wastewater treatment plants. And nitrogen and phosphorus are nutrients. You fertilize your lawn, makes it grow really nicely. Well, if you have too much fertilizer or nitrogen phosphorus in your receiving water, you'll end up with giant algae blooms, and they call that eutrophication. And you can really impact a body of water. This is what happened back in Chesapeake Bay on the East Coast. And they had a massive push to reduce the nutrients going into that body of water. And they put some very, very tight limits on all wastewater plant discharges, which cost millions and millions, billions of dollars for wastewater treatment plant improvements to meet those really strict limits for nitrogen and phosphorus. There's other things too that can impact. It can cause eutrophication and impact the receiving water, but also let's say you have perk ponds. There's some places that still have percolation ponds where they put their treated wastewater out in these ponds and they percolate down in the ground to recharge the groundwater. Well, if you have real high nitrates in your wastewater, you haven't removed that, and gets down into the groundwater and somebody's pulling that up in a well and you have very high nitrate concentrations in the well water, you can have the blue baby syndrome, it's called, where it actually interferes with oxygen transfer in the human body and in the lungs. So again, it can be very, very dangerous and a big health risk. So again, another reason to start looking at removing nitrogen in particular out of the wastewater. And the other is it can cause corrosive water conditions, especially if you're recycling water, and we do. And our water is multi-use. It's used for landscape irrigation. It's used for dual flush toilet water in new buildings of big apartment complexes and things. All the toilet flush water is with our recycled water. And also there's some industries that are using it for cooling water supply. And it can actually, if you have high nitrogen concentrations in your recycled water, and it's out there being used, especially in the industrial side or out in your collection system, it can actually be corrosive. And we've seen that, and we're actually working on ways to do it, because we currently do not nitrify, and we're looking at it seriously. And some of the price tags right now to conventionally with activated sludge to nitrify and denitrify, it's going to cost us about $100 million. So yeah, that's why we're scrambling and looking for alternatives. And there's a lot of different new technologies out there that I'm just going to touch on a little bit. But again, it can be harmful to receiving water, cause eutrophication. It can end up, if your if your surface water discharging, it can cause issues with your drinking water supply and too much nitrogen in that, which can cause health issues, and it can make your water corrosive. So just really simple, nitrification is taking ammonia, which wastewater has a lot of, and this is ammonia caused by the breakdown of urea, which is urine. And if you have food industries and those kind of things, they can also add to the ammonia concentration coming into your wastewater treatment plant. Most places are around 30 parts per million of ammonia coming in. When we have a drought here at Silicon Valley Clean Water, everybody's conserving water. We'll notice our average flow is around 14 MGD during drought conditions, and there's water conservation happening. We're down about 11 MGD, but guess what? The strength of the wastewater hasn't changed. Still the same amount of solids, still the same amount of ammonia, or the amount of ammonia. But when you take the water away from it, what happens? The concentration goes up. Ours has gotten as high as 70 parts per million. So it's a big concern of ours, and that's why we're really focusing on what we're going to do, and we're kind of being proactive and trying to move early on some type of a way to reduce the amount of ammonia we have in our wastewater stream and treat it. The other typical nitrification is you're taking nitrogen in form of ammonia in your wastewater, and nitrification process through bacterial activity will reduce it to nitrite. And what's it doing? It's oxidizing, adding oxygen, and it will end up to a nice stable nitrate molecule, or NO3. So it'll take NH4, NH3, and oxidize it to NO3. And the bacteria that does that takes it from ammonia, and you'll see it also in NH3, which is more common than NH4. There's a bacteria called Nitrosomonas, and it's this group of bacteria known as the nitrite formers that convert ammonia under aerobic conditions to nitrite and derive energy from the oxidation. So basically here you're oxidizing, you're adding your oxygen. So then you're forming nitrites. And then, okay, that's the first half of nitrification. The second half is you have another bacteria that's a little more slow growing, a little more sensitive, and it's called Nitrobacter. Nitrobacter will take the nitrite, oxidize it to nitrate. So it's a two different types of bacteria that are doing that work for you in a conventional nitrification, nitrification process. And then we have denitrification. Okay, what's that? Well, hey, we got nitrate. Well, nitrate's not all that great in high concentrations either, especially to human health and also to some of your receiving waters. So we have to get rid of that. How do we do that? Well, we denitrify. We reduce it. We have NO3, which is 3 oxygens. And then by bacterial activity, it's another type of bacteria, it will actually start to utilize this oxygen as their oxygen source. And they'll start pulling it off. And they'll start reducing nitrate to nitrite, to nitric oxide, to nitrous oxide. And then you'll end up with just nitrogen gas. And nitrogen gas just blows off into the atmosphere. So you have the first phase, which is nitrification, and then you have denitrification. And this removes all the nitrogen from your system. And this is just an illustration I found, and I find it very helpful because it's very simple, where you take your ammonia, your nitrification process to nitrate, but the denitrification process can either go back up to nitrite, and then it goes and follows the typical denitrification cycle. There's also, as we'll get to it, there's some newer technologies that are out there. Oh, this is one kind of interesting slide. If you're going to nitrify, you can actually control your nitrification through your MCRT and your water temperature. As your water temperature increases, you have more biological activity, and you can actually nitrify at a lower MCRT. This is your MCRT on top of the graph, and this is your water temperature. So as the water gets cool in the winter, you need a longer MCRT to nitrify. If the water's too cold and you have it over here at 1.2, it won't nitrify. But if you want to nitrify and the water's cold, you need more inventory. You need to keep your MCRT up a little higher. So this is just kind of something that may be useful on a essay question. So you can control nitrification based on your different seasonal water temperatures with your MCRT. And then this is a typical process that we see in conventional activated sludge. Is called the Bardenfoe process, where they actually have different zones. They have an anoxic zone, which will remove your nitrate, your NO3. And then in your aeration basin, you're going to add air. So you're going to oxidize. So this is where your nitrification happens, taking your ammonia down to nitrate. And it's followed by another anoxic zone where it will remove that nitrate, the NO3, to nitrogen gas, and then to your secondary clarifiers. So it just alternates anoxic zone, oxic, anoxic, oxic. And then that will, in one pass, both remove nitrify and denitrify all in the same process. And this is pretty popular, and you'll see a number of Bardenfoe processes around. And this is just an interesting thing that is starting to come about. And there's a special bacteria called Hamamoto, and it's a registered bacteria. It's basically it's a certain type of bacteria that feeds on ammonia. And what it does is the Hamamoto takes your ammonia and takes it to nitrite, your regular cycle. This is your nitrosomonas taking it to nitrite. And then your nitrobacter needs to come in and take it to nitrate, right? Well, Hamamoto comes in at that time and takes it from nitrate straight to nitrogen gas. So you skip, they call this nitrogen shunting. You're shunting the nitrogen cycle, the nitrification and denitrification cycle. And by shunting it, you save a lot of energy and it happens much faster. So this is something that you'll start to see more literature on. There's a number of plants that are doing pilot studies with Hamamoto. There's another one called Nitamox. There's different forms of bacteria that utilize ammonia and nitrate to basically short circuit or take shortcuts in this nitrogen cycle. And then this is typical Hamamoto, and these pictures I actually took. I visited Denmark, and Denmark's kind of the leader of the Netherlands in this technology. And what they've done is they've been able to create an environment where they grow what they call granular activated sludge, which is amazing to me. And it has Anammox bacteria in it. And basically this is a colony. This is a colony of bacteria. And the inner part here is anoxic. And it's actually taking your nitrate and denitrifying. And your nitrifying bacteria are on the outside because they're exposed to oxygen. So that one granular, like a rice grain, the outside of the rice grain is nitrifying, and the inside of the rice grain is denitrifying. So you have one colony of bacteria that's in a granular form that's doing all the work in the same tank at the same time. So that reduces the amount of tankage that you need. It reduces the amount of oxygen and energy you need to put into it. It's very, very efficient. But again, the Danes have figured it out. They're very successful at it. Over here in the States, we're a little slower learners, and we're just now getting up to speed on it. And we're starting to see many more plants starting to look in this direction for nitrification and denitrification. And that's all I got for you today. Hopefully it was some information that's going to help you in your exams. If you got any questions, happy to answer. Also, my contact information was on the front part of the slides. Feel free to reach out. I'm usually around. Again, been nice meeting everybody, and best of luck.
Thank you very much, Monte.
All right. All righty, Dwight.
Thank you, Monte.
You're very welcome, everyone.
Great job, Monte. I guess, Jordan, you'll be up next if you're ready, if you're here.
Yep, I'm going to quit sharing and log off. Hey, Jordan.
Monte.
All righty.
Good work.
Good to see you. Good luck.
ya.
All right.
All right. Can everybody hear me okay?
Sounds good.
Yep.
Perfect. Well, welcome to the part 2 of our wastewater session today. It's nice to be with you all, and I'm going to spend the next hour or so talking about clarification, primary and secondary clarifiers. Not repeating any of the activated sludge stuff that Monte just talked about, but we'll try to connect the dots to some other processes as well. As you all know, when you get to the higher grade level exams, there's more of a critical thinking component, right? You can't just memorize facts and figures and regurgitate that and expect to do well. You have to be able to draw connections between different parts of the treatment process. And so that's what I hope to do today as we talk through, you know, what is a relatively basic process of clarification, try to connect the dots to some of the other processes in the wastewater system, and help you understand how to make those connections and how things link together. We'll also spend a bit of time today talking about the math that is relevant to clarifiers. I find that people get the most nervous and hung up on the math part, so we'll spend a little bit of time going through some examples and talk about, you know, what that means for your operating, how you make decisions based on the outcome of those math problems. So let me find my clicker here. Here's my contact information. I'm the district engineer for the Fairfield-Suisun Sewer District. I'm a registered engineer, licensed operator. That's due to the hours requirements, but I have taken the grade 5 exam and passed. And I've been working in the industry for about 14 years. Here's my contact information. If you have any questions after today, feel free to reach out, send me a message. I'll get back to you as soon as I can. The goal for today is to, you know, really understand primary and secondary clarifiers, what their purpose is, how they function, identify what we can see that will tell us that they're performing well or that they're not performing well, and how would we go about correcting that. We want to be able to identify a poorly performing clarifier and take corrective action. and we want to understand the math and really understand what the math tells us about how the clarifier is functioning. And so here's a general overview of what we're going to talk through today. We're going to go real quick through the beginning parts because I know you all already have wastewater licenses, so that'll just be a quick refresher, and we'll spend most of the time on the math problems and the critical thinking associated with that. So this should, again, not be a surprise to anyone. There are different types of contaminants that we're trying to remove in wastewater treatment. And these are sort of the three big categories. The first is solids, the second is BOD, or biochemical oxygen demand, and the third is pathogens. And so what I want you to understand here is that when we talk about a primary clarifier, it's really helping us address all three of these contaminant forms. We usually think of a clarifier really as a settling tank for solids. So obviously, physical removal of solids is occurring, and that's the primary thing that's occurring. But what we also need to understand is that a large portion of those solids are made up of biochemical oxygen demand. So a primary clarifier is actually kind of a secondary process to remove BOD from our wastewater stream. It's not the main focused process like activated sludge that you just learned about, but important to remember that the primary clarifier plays a critical role in BOD removal as well. And the other thing to remember is that pathogens, things like large bacteria, they are solids, they're particles in and of themselves. And so if we have a process to remove solids from wastewater, we're also going to remove some of those pathogens. So I just like to start with this to remind everyone that although a primary clarifier is, not at face value, it doesn't seem like the most exciting wastewater process. It really is a critical component, and it addresses a lot of the problems we're trying to solve in wastewater treatment. And so, it's important to understand, and you'll almost certainly have to explain this and write about it on your grade 4 or grade 5 exam, of how well the clarifier performs at removing different sorts of contaminants. So first of all, when we talk about BOD, the biochemical oxygen demand, we're going to typically get between 25 and 40% removal of that BOD just in the primary clarifier. That's with no biological treatment. So that's a great jump start to the BOD removal process. When we look at solids, there's a lot of different types of solids, as you all know by now. Firstly, we have dissolved solids. These are very tiny solids particles that are literally dissolved in the water. You're not going to be able to easily separate them from the water. And if you set a glass full of dissolved solids on the counter for days, there will be no settling. These solids are so small that they are basically held in suspension by the chemical interactions between water molecules and solids. So we're going to get very little removal of those because a primary clarifier is just a big settling tank. And if these materials don't settle, then we're not going to be able to get rid of them. The other element of solids is suspended solids. So total suspended solids is really the bread and butter of the primary clarifier process. We're going to remove between 50 or 75% of the TSS, the total suspended solids, in the wastewater. Now, TSS can be categorized as a couple different subcategories, and I kind of simplify this as things that sink and things that float. So floatable solids, what we call scum, that's things like fats, oils, and grease, certain kinds of plastic materials or trash debris. Those materials, if you put it in a big open tank, they're going to tend to rise to the surface, and we can scrape those off the top. The rest of the total suspended solids are what we call settlable solids. And so those are solids that, given enough time, will slowly sink down to the bottom of the water. And so that's what we're trying to remove in wastewater treatment. We can remove over 90% of those settlable solids from the flow. And so I just want to touch real quick and remind you on the relationship between solids and BOD. So what I've got here is a Venn diagram. Hopefully you've all seen a Venn diagram, right? It helps illustrate an overlap between two different groups of things. So I've got two circles here. One represents all the biochemical oxygen demand in your wastewater, and one represents all the suspended solids in your wastewater. Now, if I focus on the BOD, BOD can be categorized in two parts. We've got soluble BOD, so that's BOD that is dissolved in the wastewater. And then we've got particulate BOD. So that's BOD that's integrated into solid material. So this could be something like a bacteria cell, right? A bacteria cell is largely organic. It's going to require oxygen to degrade, but it is a solid. So it's going to fall in this overlap portion of particulate BOD. Now, if we look at this from the suspended solids perspective, we have a couple subcategories of suspended solids as well. A lot of the suspended solids are what we refer to as inert or non-reactive. They're not going to interact with any biological or chemical process. So an example of an inert suspended solid would be a grain of sand, right? It's mineral, it's mostly made of rock. It's not going to react to a bacterial process or a chemical process. It's just there. But the other form of suspended solids are the biodegradable suspended solids. So again, this would be a suspended solid like a bacterial cell that is a solid. It's a particle, but it is organic and it will biodegrade through the wastewater process. And so really what we're targeting in a primary clarifier is this overlap area. It's the suspended solids that are, let me rephrase, it's the BOD that is bound up in suspended solids, and therefore that's the portion of the BOD that we're going to remove from the wastewater. And this is just a picture graphic, but remember it's about 25%, say, of the BOD will get removed in the primary clarifier. Okay, so why do we clarify? We talked about it a bit, what we're trying to address, but what are we trying to accomplish here? So we locate the primary clarifier after preliminary treatment. So we do the headworks screening and grit removal to try and remove some of the larger non-organic material that would otherwise settle in our primary clarifier. We want to get it out beforehand. So screening and grit removal will remove that large debris from the flow. And then we're building our primary clarifier process to remove the settleable suspended solids and those floatable solids that rise to the surface of the water. And the great thing about a primary clarifier is that if you design it right, the solids that you remove from that process are mostly organic, right? They have a lot of carbon in them. And organic materials have a lot of stored energy inside. And so that's why the primary sludge that we generate from a primary clarifier process is what often gets sent to an anaerobic digester for further breakdown and ultimately, the production of biogas that can be used for energy generation or vehicle fueling. Really exciting uses of what is otherwise a waste product for renewable purposes. And so in my little reddish pinkish box here at the bottom, I want you to think about, how a test question could be worded on the grade 4 or grade 5 exam that where you have to draw a link between the primary clarifier process, in other words, the sludge that we're producing, and the anaerobic digestion process, which is where you're feeding that sludge and how much energy you might generate from that. So, we like to think about the treatment plant in terms of these separate areas that each function individually. And while that's true to some extent, there are links, and So keep that in mind as we talk through today. Looking at secondary clarifiers operate very similarly to primary clarifiers, but they are generally located after a biological process. So those biological processes, such as activated sludge that Monte just talked through for the last hour, or even a trickling filter, these processes are converting your soluble or dissolved BOD, they're converting it into a solid form. Basically, the bacteria is growing while it consumes the dissolved BOD. And so we need a physical process to separate that material from the wastewater flow. And so we do that with a secondary clarifier. We're separating the MLSS, the mixed liquor suspended solids, from what is now low BOD, relatively clean effluent. And then the other thing that the secondary clarifier does is we're really trying to target a concentration of return activated sludge. So we want to send a nice concentrated stream of bacteria back to the front end of the process so that it can be used for eating new BOD that comes into the process. So it really increases our efficiency. It allows us to clean the water in a much faster time and a much smaller footprint by having a good, high concentrated return activated sludge. And so you've, I think, just talked about that a fair amount. So I won't get into too many more details, but if anyone has any questions, feel free to type them in or shout them out. Okay, now I'm not going to spend much time here at all because I'm assuming at this point, if you've made it through your grade 3 license, you understand how clarifiers work. But suffice it to say, we're feeding raw influent to the tank. We're expecting primary sludge to settle to the bottom of the tank and be collected in order to be pumped onto a digester, for example. We're expecting scum or floatable material to float to the top of the tank where it can be skimmed off and again sent to a digester, for example. And then we're expecting an effluent product, our primary effluent, that has largely been treated of suspended solids. So we would expect a very low concentration of solids coming out of the tank, and we would expect a slightly reduced amount of BOD because we've removed about 25% of that in the primary clarifier. Okay. Now, secondary clarifier works very similarly. The only difference is we're feeding it mixed liquor suspended solids. So we have this high concentrated bacterial soup that we just generated in the activated sludge tank. And now we need to separate the solid material from the liquid material. So the sludge is going to settle to the bottom. We'll have very low BOD, low TSS effluent overflow the top of the tank. And that'll be our clean effluent that goes on to either onto your disinfection or perhaps more filtration or other advanced treatment. And then we collect the sludge on the bottom where we send it to one of two places. Either that sludge gets returned through our return activated sludge line. See if that helps. We send that sludge through the return activated sludge line where it mixes with new influent and feeds back into our aeration tank for additional BOD treatment. Or, as you all hopefully understand by now, if you just keep returning all of the sludge, your concentration is going to grow higher and higher and higher because there's no outlet for that sludge. So in order to control our mixed liquor suspended solids concentration to a specific point, we have to waste any new material that's produced. And so we've got this line shown right here, the waste activated sludge line, which is how we essentially throw out the extras that we don't need and maintain a consistent level of mixed liquor suspended solids in our activated sludge process. Okay, so in both cases, we're separating solids from water is really the ultimate goal. And whether that's by sinking to the bottom or by floating to the top, we're collecting the solids in a specific location where we can easily remove them and send them on to the next process. Keep in mind also that our waste activated sludge is also mostly organic, mostly biodegradable, because it is bacterial cells, right? It's the mixed liquor bacteria that we have wasted now. And so similar to the primary sludge, this sludge has a lot of energy bound up in it, and we can take advantage of that in a process like anaerobic digestion, where we degrade that biology into its constituent parts, generating methane gas, which we can then use to power a cogen engine, for example, and offset our power costs. Okay. Oops. Okay, so we're going to get into a little bit of the math here. And so some of this math, is very specific to clarifiers, but some of it is more general. And so I'll try to point out where these formulas are more general, and you might see them elsewhere on the test other than just talking about clarifiers. And this is one of them, the efficiency formula. So we can measure an efficiency on almost every process in the plant. That's how we know that the process is working right. Every process is designed to remove something from the wastewater stream. And so the efficiency is a way to measure how good are we doing at removing that thing that we're supposed to remove in this process. So for a clarifier, we care about the removal of suspended solids. So we can calculate an efficiency using the following formula. We take the concentration of whatever it is we're trying to remove that's coming into the tank. We subtract the concentration that's going out of the tank, and we divide it by the concentration that was coming in. And then we multiply that by 100 to convert from a decimal to a percentage. Okay, so if this is my primary clarifier, I've got some amount of suspended solids that's flowing into the tank. I'm collecting a lot of those suspended solids on the bottom of the tank where I can pump it on to my digester. And then I've got a relatively low amount of suspended solids leaving at the back end of the tank. And so if I compare the in and the out and plug them into my efficiency formula, I can assess how good I'm doing at removing material. So what do these concentrations look like? For a typical wastewater coming into a treatment plant, we might see an influent suspended solids concentration between 200 and 300 milligrams per liter. Obviously, these can vary, right? Depends on where you are. It depends on what industries are in your service area. It depends on how strongly your area is conserving water. I think Monte mentioned that before with ammonia coming into the plant, that as more and more customers are conserving water, and as our state is really, enforcing water conservation because of the drought, that doesn't mean that the amounts of waste coming down the sewer are any less. It just means they're being carried by less water. So the concentrations go up, even though the flows go down. So we might see 200 to 300 milligrams per liter of total suspended solids coming into the plant. We might see, depending on your area, these numbers are a little high, but we might see upwards of 500 to 700 milligrams per liter of VOD in certain situations. And just again, this is a repeat of what we saw in the prior slide. We're looking at about a 50 to 75% removal of suspended solids, a 25 to 40% removal of VOD. And those settlable solids, we're going to remove almost all of them, 90 to 95%. But remember, these are the removal efficiencies for an optimal performing tank. And that's our job as wastewater operators, is to make sure that we are allowing this process to function optimally. So the note I have at the bottom here is we can only get the removal efficiencies stated above if we manage the process so that the water stays in the tank long enough to allow all of that contamination to settle out. And so that's our goal. And a lot of the remaining time today, we're going to look at formulas that can help us understand if we are stressing a process to the point where it may not be performing as well as we want it to. Okay. So here's an example problem. What is the TSS removal efficiency of a primary clarifier if the influent TSS is 250 milligrams per liter and the effluent TSS is 83 milligrams per liter? And then part 2 of the question, and this is the part I add on for the grade 4s and grade 5s, is you don't just do the math, but now you have to explain to me, is this clarifier performing efficiently? And those are the types of things that they're going to ask you, is to not just crunch the numbers, but to take it the next step and draw a conclusion from those numbers. So let's work through this example here. So here's my efficiency formula, right? I've shortened it a little bit. What comes in minus what goes out divided by what goes in times 100. So I plug in the numbers from the problem, right? This is a relatively simple math problem. This may have been asked on your grade 2 or grade 3 exam. You follow through on the math and you get 66.8% removal efficiency of total suspended solids. But again, we're taking grade 4 and grade 5. So the question is, if you were an operator and you calculated your removal efficiency as 66.8%, are you going to change anything, or is it working well? So remember, on the prior slide, we talked about a typical suspended solids removal in a primary clarifier is between 50 and 75% removal. So that's going to be our frame of reference to answer questions like this. We know what the conventional average is, and we need to compare our performance to, the standard performance that's been measured over the last 120 years of wastewater treatment, right? Wastewater treatment's been operating largely the same for over 100 years now, so we've got a lot of historical data to go off of. So if I'm supposed to be in the 50 to 75% range and I'm removing just under 67%, then I would say this clarifier is performing within the parameters of normal operation for a conventional primary clarifier, right? And so that might be something that, for example, you have to write a paragraph on. This could be an essay question. Explain, you calculate this efficiency, explain why or why not that this clarifier is performing correctly. And so having some of these references, understanding what the removals should be, can help you assess whether a process is working well or not. Make sense? Okay. So the next parameter that is really important for, for a lot of processes really, but especially for clarifiers, is detention time. So the detention time is the average amount of time that a drop of water or a molecule of contaminant is going to spend in that clarifier. Now, it's important to remember that detention time is a big average number, right? We're not actually measuring a drop of water. We're taking the geometry of a large tank and the flow that's coming in, and we're calculating an average. So you could have 2 tanks with the exact same detention time that perform very differently depending on how they're designed, how they're configured, and how they're operated. So keep that in mind too. The formula for detention time is, hopefully this is a refresher, you take the tank volume and you divide it by the influent flow rate. And if you keep track of your units, and I will, if Monte and others haven't already beat this into your head, I will strongly reinforce and request that you always write the units next to your numbers. I've seen so many people get tricked up on a problem because they're not keeping track of units. Units are, I always say it's a form of checking your own work, because if you follow those units through and make sure that they cancel out in the right way, you'll know that you've probably done the problem right if you end up with the right units. If you end up with some wacky units like, I don't know, cubic feet squared over seconds, that's not a real thing. And we know that that's a nonsense unit. So we've probably plugged the numbers in wrong into our math equation. Okay, so always keep track of units. If you do the units right, you'll find that detention time comes out in units of time. So you're going to get, you know, hours or days or minutes. That'll be the measurement of the detention time. And that represents the average amount of time that a drop of water is going to spend in that tank. But as I mentioned before, certain tanks might have short circuiting. So if you have a tank that's poorly designed and some of that flow is just kind of cheating and shortcutting from the entrance of the tank to the exit of the tank, some of that water is not going to be meeting this theoretical average detention time, which means your performance is going to be worse. So how could we use this information? I would say if you calculated detention time and your detention time is, you know, appropriate for what you're trying to achieve, but you find that the process is still not performing well, you might want to look at the geometry of the tank and short circuiting as a possible solution. Sometimes just installing a baffle in the tank to not allow water to short circuit, to force it to mix into the full tank is all you need to do to really improve your performance. Okay. Just a little bit more about units. These are some examples of how you might calculate detention time. So for example, if I'm given the volume of a tank in gallons and I'm given a flow rate in gallons per second, well, I want to make sure that the volume units match up so that they cancel out. So I need gallons and gallons, and I want to make sure that the time units match up, seconds and seconds, right? So if I'm given a problem where I have gallons in cubic feet per minute, well, I'm going to need to do some unit conversion in order to make sure that the volume units will cancel out, and then know that my detention time is going to be calculated in whatever the time unit of the flow rate is. So here's another example. I could be given the volume of tank in cubic feet and the flow rate in cubic feet per minute. And again, as long as those volume portions in red are the same units, then I know that my time unit is going to be equal to the time piece of the flow rate. Okay, so this is a quick double check to make sure that you've done the math right. And just a good thing to think about to make sure that you've got the right units. Remember that, so let's take the second one, for example. If I'm given the volume in cubic feet and the flow rate in cubic feet per minute, but the question asks me to find the detention time in hours, well, I can go ahead and do the math this way, get a detention time in minutes, and then at the end, convert minutes to hours. And that's just basic unit conversion. Hopefully you're well-versed in that from your prior certification tests and your jobs. That is you can always do the conversion at the end. So why is detention time important? Well, as we talked about, detention time could be too short, right? If you're not letting the wastewater sit in the tank for long enough, you're not going to get as good removal as you want to get out of your primary clarifier. But also when we start talking about secondary clarifiers, detention time is really important because the longer you let the sludge sit, the more time it has to use up all of the oxygen that's available in the wastewater. And as you hopefully know, and I think talked about a little bit last hour, when mixed liquor suspended solids go anaerobic, when they no longer have any oxygen present, they start doing funny things like denitrifying and producing nitrogen gas. And nitrogen gas is a gas, so it's lighter than water, it bubbles up to the surface, and it usually carries clouds of sludge with it. So if you start seeing this in your secondary clarifier, where you get these big cloudy bubbles of sludge coming to the top, you know that you're probably operating with too long of a detention time. You're letting the sludge sit there too long so that it uses up all the oxygen and starts denitrifying. In a lot of cases, especially with new nutrient regulations, we want to denitrify. That's a good goal, but we don't want to denitrify in the secondary clarifier. We want to denitrify in the aeration basin in the process that's designed to denitrify. The whole point of a secondary is to let all the sludge settle to the bottom. So if you have anything like this where that sludge is bubbling to the top, you're fighting against the whole goal of the process. So that's an example of too long of detention time. The primary clarifier example where we're not removing enough suspended solids is an example of a too short of a detention time. So it can go both ways. So here's a simple example. I'm going to click through this really quick. You'll hopefully be able to download a copy of these slides, and you can work through this a little slower on your own later. But if we've got a tank that is 1,500,000 gallons, and you're receiving a flow of 12.5 million gallons per day, find the detention time in hours. So we're going to do some unit conversion to make the volume units consistent. I'm going to plug that into my detention time formula. Got 1.5 million gallon tank volume divided by a 12.5 million gallon per day flow. Again, I know my volume units cancel out, and so the time unit that I'm left with is going to be the unit for my answer. So plug those into my calculator, I get 0.12 days. You might think you're done, but as I always remind everyone, when you think you're done, go back and read the question one more time and make sure that you've actually answered what they're asking for. So when I read this again, I see, what is the detention time in hours? Well, I've only calculated it in days. So I need to do one last unit conversion step to convert units, to convert the day units to hours. And I find that that's 2.88 hours detention time. Okay. So the next element to help us understand how our clarifier is performing is called surface overflow rate. Surface overflow rate is a measure of the hydraulic loading. So in other words, how much water we're putting into the tank. And we measure that using this formula. We take the influent flow to that tank and we divide it by the surface area of the tank. So this is always one of those points where I want to stop and remind you that this is the top surface area. This is the area you would see if you were looking at Google Maps, right? It's the overhead view. Surface overflow rate has nothing to do with the depth of the tank. This tank could be 1 foot deep or it could be 100 feet deep, and it wouldn't matter. The surface overflow rate would be the same calculation, okay? So just keep that in mind. Make sure you're using the right area. The units of surface overflow rate typically are going to be measured in gallons per day per square foot, okay? And so again, like detention time, this number doesn't really mean anything unless you compare it to an industry standard clarifier. And so one number you might want to keep in your head, or one set of numbers you might want to keep in your head, are that for a typical clarifier, your surface overflow rate should be between 800 to 1200 gallons per day per square foot. And so given any situation that the water board could think of to throw at you in a test question here, you should be able to calculate the surface overflow rate based on the flow rate and the geometry of the tank. And you should be able to compare that to a typical clarifier performance between 800 and 1200 gallons per day per square foot. If the surface overflow rate you calculate is higher, that means you are hydraulically overloading the tank. That means you're pushing more water through the tank than it's really designed to handle. And so what's the impact of that going to be? Well, usually the impact of that is you're shortening the detention time. You're not allowing enough time for that water to settle because you're just pushing so much water into the tank. And so what we're going to see in those examples is you're going to start to see solids wash out, where your solids concentration in the effluent is going to go up and up and up because you're not allowing it enough time to settle out. You're stressing the tank process, okay? So how do we resolve that if our surface overflow rate is too high? Well, there's really only a couple things we can control. We could decrease the flow, right? So that we're not pushing as much water into the process. But that is not always under our control, right? If it starts raining and the flow goes up, it is what it is, and there's not a lot we can do about it. So the other thing we can do is change the surface area. And again, I'm an engineer here, so if you call up your engineering department and say, hey, I need a new tank and I need it within a couple hours because my surface overflow rate's too high, that's not gonna work. That's like a 2-year project for us, and it costs a lot of money. So what the thing that an operator can control is how many tanks are in service. So if you have, say, 4 or 5 primary clarifiers, you might take some of those clarifiers offline in the summer, say, for maintenance, right? We don't need all these tanks, the flows are lower, but you might hit a point where your surface overflow rate starts pushing up against the upper limit of how hard we want to push a clarifier. And so as the plant operator, your job is going to be to understand when it is appropriate to put on that next tank and basically divide the flow now between more tanks. And that'll decrease your surface overflow rate in each one. Okay, does that make sense? So I just talked about this a little bit. Yeah, if the surface overflow rate is too high, you can either reduce the flow. If you have raw influent equalization or something like that, you might be able to do that. The only other way is to put more clarifiers in service. And I talked a little bit about the relationship between surface overflow rate and detention time. Basically, if you're hydraulically overloading a clarifier, you are negatively affecting both the surface overflow rate and the detention time. So we, for proper primary clarifier operation, we're usually looking at 1 to 3 hours of detention time in that 800 to 1200 gallons per day per square foot of surface overflow rate. So just with those 2 parameters alone, you can really start to dissect how well your process is running and see if you need to make any changes to improve your removal efficiencies. So again, here's a quick math problem. If you have a tank measuring 125 feet by 25 feet and you see a daily flow of 5 mgd, so you're going to calculate the surface area. That's just a area of a rectangle. Convert the flow to gallons per day, and then divide the influent flow by the surface area. Plug in those numbers, and you get 1,600 gallons per day per square foot. So what can we say about this primary clarifier? Well, we know that no, I can't click back, that'll take me too long. Our standard is 800 to 1,200 gallons per day per square foot. This clarifier is seeing 1,600 gallons per day per square foot. So we're overloading this clarifier, we're pushing too much water into it, and it's probably not going to perform very well. Okay. So just from this quick word problem, again, you could see an essay question on your exam that asks you to explain if this process is functioning well and what you might do to fix it. So there's a couple tips. You can calculate surface overflow rate, see that it's hydraulically overloaded, and then describe some of the things you might do to correct hydraulic overloading of a clarifier. Okay, this is just another example. You'll have this for your notes, but for the sake of time, I'm going to click through it quickly. Another example of a metric we can use to evaluate clarifier performance is called the Weir overflow rate. This is a similar measurement of hydraulic loading, but instead of the total surface area of the tank, we just look at the length of the effluent weirs. And so again, we have to have a standard to compare this to. So for a conventional primary clarifier, A typical Weir overflow rate is between 5,000 and 15,000 gallons per day per foot. And that's per foot of Weir length. So similar to surface overflow rate, if we have a high Weir overflow rate, it means that we're hydraulically overloading the tank. What it means really is that the water velocity over the effluent Weir is going to be very high, which is going to tend to carry solids along with the flow, right? The faster the water is moving, the more it's going to grab on to those solids that it flows by and carry them out of the tank. And again, our whole point here is to keep the solids in the tank and have nice, clean, clear effluent flowing out the backside. So if we overload, we run the risk of having higher solids concentration in our primary effluent. And so for Weir overflow rate, we're going to take the influent flow to the tank and just divide it by the total Weir length. And so remember that the Weir length is the total length of Weirs that the water can overflow in order to get into, get out of the tank. And so, see here, just going to see if I could just draw on this real quick. So if I have a tank here on the left with two horizontal launders, I'm going to assume that water can overflow on both sides of each of these launders, right? And so when I'm calculating my total Weir length, it's going to be the length of this launder times 4, because I've got 4 sides where water is overflowing. In this example on the right, if I've got 3 effluent launders, again, each one has 2 sides. So my Weir overflow length is going to be the total length of the launder times 6, because I'll have 6 sides that are being overflowed. And then remember that some clarifiers have perpendicular weirs or perpendicular launders. So if you've got a tank where the weirs go side to side instead of front to back, it's the same formula. You just count how many sides are being overflowed and multiply it by the length of the weir. In this case, the weir length is going to be the width of the tank, because they go crosswise instead of lengthwise. Okay. And then remember that, for example, in a secondary clarifier, those are often circular. So when you're calculating your weir length, you're probably going to use a circle geometry. Find the circumference of that circle, and that'll be your total weir length. So again, here's an example. I'm just going to click through this, but you'll have it for future. The next parameter we're going to talk about is called solids loading rate. So remember, with surface overflow rate and weir loading rate, we were talking about the hydraulic loading of that tank, right? The water that we're pushing into it. But what that doesn't take into account is how dirty that water is. So we also have to look at the solids loading rate, because if we end up pushing very dirty, high solids water into the tank, we're not going to be able to push it as hard as if that water had pretty low solids to begin with. Because again, there's just more solids to deal with, and we need to give them all enough time to settle to the bottom of the tank. So solids loading rate is calculated very similar to surface loading rate, except that we use the pounds of solids being sent into the tank instead of the gallons. So again, a typical value, something we want to compare to, is 25 to 30 pounds of solids per day per square foot of surface area of that clarifier. But this is going to change, right? Your solids loading rate is going to increase and decrease as your flow increases and decreases. So for short amounts of time, we might see a peak value upwards of 50 pounds per day per square foot. And so the formula for solids loading rate is we just take that pounds formula based on the flow and the concentration of solids coming into the tank, take the pounds of solids and divide it by that surface area of the tank, just like in surface overflow rate. Okay. So again, here's a example solids loading rate for a clarifier that has a 22-foot radius and a depth of 8.5 feet and receives a flow of 1,450,000 gallons per day with a suspended solids concentration of 3,400 milligrams per liter. So first thing we want to do is calculate the clarifier surface area. That's pi r squared. That'll be on your formula sheet that you'll have access to during the exam. Then we want to calculate the percent solids. So this is, again, another formula that's on your formula sheet. I kind of glossed over it for now, but you can take the concentration and divide it by 10,000 to find the percent of solids. So here I have 0.34% total solids. Then I calculate my pounds per day. And when you crunch that through, I get 41,000 pounds per day. And so to calculate the surface loading rate, I take the pounds per day of solids, divide by the surface area of the clarifier, and I get 27.1 pounds per day per square foot, which, if you remember, our sweet spot is in that 15 to 30 pounds per day per square foot range. So this clarifier is kind of towards the upper end, but it's still in the acceptable range of solids loading. Okay. And again, I understand I'm clicking through these very quickly, but you will have the ability to download these slides and work through them at your own pace later. So the next thing that I think is, very fair game for a grade 4 and grade 5 exam is to really start talking about the sludge withdrawal rate. So everything we've talked to so far talks about the performance of the tank itself in removing solids. But keep in mind that we have to do something with those solids, right? We can't just let them build up at the bottom of the tank and keep collecting, because sooner or later it's going to fill up and overflow and we'll have very poor performance. So we're going to have some sort of sludge pumping that will pump the settled sludge out from the bottom of the tank. And there's a lot of questions, a lot of math that could be tested on sludge withdrawal rate. So this is something I would suggest you spend a little time on in your preparation. Generally, when that sludge settles, it's going to get scraped either in a round clarifier. There's the circular mechanism that'll scrape it to the center, or in a rectangular clarifier, there'll be a chain and flight system that scrapes it all back into a pit or a hopper. So that sludge is going to be collected somewhere, and we're going to pump from that sump or hopper onto wherever it goes next. Could be a digester, it could be a drying bed, could be a dewatering process. If given enough time to settle, so if our clarifier is performing well, we will see that the primary sludge is usually concentrated to about 3 to 7% total solids. Okay, it's going to depend a little bit on the nature of your plant and the nature of the sludge, but 3 to 7 is a pretty normal range. So we could just turn on a pump full blast and just let it pump out of that sump all the time. Anytime any bit of solids gets into that sump, it gets pumped out, right? That's one approach. But here's the problem. If we end up pumping too much, we're not going to be pumping many solids. We'll be mostly pumping water because we're not allowing the solids enough time to concentrate. Now, pumping water isn't necessarily bad, but if we're sending the sludge onto a solids treatment process, such as a dewatering process or a digester process, we would really prefer just to have the solids and less water. So pumping water is usually bad for our downstream solids treatment process, okay? So it's really important not to just let the pump pump. You're usually gonna have it on a timer where it turns on and off periodically to allow time for the sludge to concentrate, and so that we're pumping, more sludge to the next process and less water. But on the other hand, if we pump too little, then that sludge that's just sitting there is going to start to break down, go anaerobic, and produce gas. That can cause odor issues, that can cause poor settlement. The sludge blanket can also start building up higher and higher and higher. And again, now we're filling up our tank volume with solids and having less time for settling. We're basically shortening the detention time by creating a smaller volume. And then eventually, if the sludge gets high enough, the velocity of the water is just going to carry it right over the effluent weir. And again, we're basically canceling out any good that the clarifier was intended to do. So it's a sweet spot. We got to find that spot where we can pump continuously at 3 to 7% solids, reduce the amount of water we pump, but not let the sludge blanket build up too high to cause other problems. Okay. So when we talk about total solids of the sludge, remember that sludge is made up of two parts. When we say sludge, we just mean it's solids mixed with water. So when we talk about the weight of sludge, we've got the weight of the solids, and then we've got the weight of the water that is in that sludge mixture. And so if you do some mathematical exercises here, you can find out this formula for percent total solids is just the total solids weight. So that's not including the water, just the solids, divided by the sludge weight. What the percent total solids tells you is for a given volume of sludge, how much of that is solids, and then the rest is going to be water. So if I have a primary sludge that's at 3% solids, that means 97% of the weight is water and only 3% of the weight is solids. Okay. So there's a quick calculation you can do. This is mostly just dimensional analysis, right? Unit conversion. But you can figure out what the total weight of solids that you pump per day. And that's a number that could be very useful for a digester problem, is knowing how many pounds of solids you're sending to the digester so that you can figure out how much gas you're going to produce. And then real quick, I know I've got just 1 minute left, so I just wanted to remind you, again, this is going a little bit beyond clarifiers, but I think important to everything we do as operators is considering the electricity costs, right? Electricity is very expensive. And so anytime we're pumping, we're spending electricity, and that's costing us money. And so I wanted to remind you, I pulled these from the formula sheet that's on the state board's website. Remind you that there's a factor to convert horsepower to kilowatt hours or to kilowatts. That's how you calculate power cost. And then there's a whole bunch of things with pump efficiency that you need to understand. One of which I'll just go through here real quick, and then I'll be done. Remember that when we have a motor system, or a pump and motor system, so here's the pump, here's the motor. When you talk about horsepower, there's a lot of different elements. The water horsepower is what you actually need to put into the water to pump it to whatever pressure at whatever flow you want. But because a pump is not 100% efficient, the pump itself is going to use up some of the power. So we have this thing called brake horsepower, which is the input power to the pump to give you a smaller amount of output power. And then same thing on the motor, it's not 100% efficient. So your motor horsepower or electrical horsepower is going to be higher than the brake horsepower that comes out of it. And remember that motor horsepower, that's what we pay for, right? We pay for the amount of electricity we draw from the power utility, even though we only get the water horsepower out of it, which is a smaller number. And that's all about efficiency. So I've got one more example here of some efficiency calculations that you can review in your own time. And sorry for going a minute over, but I hope that was helpful. Really wish you all the best in your upcoming exams, and happy to answer any questions that you might have.
Thanks, Jordan. Any questions, anyone? Just unmute yourself and ask if you have.
Thank you, Jordan.
Absolutely.
All right. Any questions? All right. You will see in your chat. We want to thank Jordan and Monte for these great presentations and taking their time sharing their experience and knowledge. thank you for attending today. And we appreciate your aspirations to move up and move on into your certifications. And we thank you for that. In the chat, I put the presentations, both Monte's and Jordan's is there, as well as a survey that we like to get your thoughts about today's session. We really want to hear that. And hopefully you'll be able to complete that. You also will receive the survey via email. And you can complete it that way as well. So at this point, I'm going to ask one more time, any questions or comments from anyone? And I'll ask.
Great. It was real helpful. Thank you.
Wonderful. All right. Jordan, any final thoughts you'd like to share before we close today?
Just to say, we're really excited to have you all move up in your certification level and move up in our industry and hopefully be, supervisors, managers, directors at some point here in the near future. So looking forward to all of your success, and feel free to reach out if you have any questions.
Great. Thanks, Jordan. All right, everybody, this will conclude our session for today. Again, the presentations is in the chat, and the survey is there, and we will be putting the recording of the sessions today on our website within a few weeks here. And so you can look for that. Stay tuned for future Baywork events, and we look forward to seeing you guys soon, and continue to be the great water professionals that you are. Have a great day.